Welcome back. So in the last class, we started discussing about spin echoes, which are very important in understanding the spectra editing. I wanted to see what is going to happen in the heteronuclear case when I apply a spin echo sequence on carbon 13. At the same time, I want to see the decoupling of proton and see what is going to happen. Of course, I was trying to explain what happened to this pulse sequence based on the vector diagram. First thing I told you, if you please remember, I applied a 90-degree pulse, brought the magnetization from z-axis to x-axis. Okay, from z-axis to x-axis. Now the spin vectors start moving, and after exactly apply a 180-degree pulse that is along this axis, I can rotate it like this. Now the spin labels get interchanged. One which is moving faster starts moving slow. One which moves moving slow starts moving faster. They will now start after exactly same amount of time. They refocus along the other axis. In this axis again they get refocused. This I said as chemical shift refocusing. When I took the example of CH vector, now we have only the two components because of alpha and beta components of carbon 13 due to its coupling with proton. Now alpha component is moving like this, beta component is moving like this. One is faster, other is slower. Now what happened to this vector, as if how much it has moved as a function of time delay. This we understood. This depends upon pi into Td into JCH. That is the equation to say how much it has moved. Okay. Now we found out if exactly tau delay is equal to j by 2, plug it into the equation. Okay, theta is equal to Td, your j by 2 you are going to plug it in, and you find out exactly at 45 degrees what is going to happen, what is the angle theta. And when 90 degrees is there, what happens? When 180 is there, happens what happens? Like that you can keep on monitoring the signal intensity. As I said, this equation pi Td into JCH is equation. I plugged into that equation and found out what happened to the magnetization as a function of Td. And we observed for a CH vector what is happening. When Td is exactly equal to 1 over j, we resolved it to a vector into two components. We said opposite moving component get nullified. The vector moving in the same direction gets added up, and we found out what is the signal. We saw when exactly this is equal to 1 over j, signal is 0. When Td is exactly equal to 1 over j, you see, Td is exactly 1j, signal is negative maximum, and this evolution of this magnetization as a function of Td follows a cosine curve like this. You understand? Now we understood what is going to happen. With this, we assumed also JCH is nearly same. It is not different. That's what we assumed. Okay? Or we can take the average value of them. Now we will see what happened to the CH2 carbon in the same pulse sequence, echo sequence. Now what is carbon here? Carbon is split into a triplet because of CH2. Two protons are attached to it. Remember. So as a consequence, it is going to be a triplet. So now I resolve three components. One is a fast moving component, a slow moving component like this, and the central component do not persist at all. It is like that. It doesn't move. Remember, one is at 0, other is plus j by 2, other is minus j. Three components. When there is a triplet, if you consider for the CH2 carbon, when the carbon is a triplet, the central component do not persist. Only outer components start moving. Okay. Now exactly find out the situation, plug it into the equation. What happens to these components at 1 over j, 1 over 2j, and at what happens after J. If you plug it and understand, exactly after half J, these two vectors will come in the opposite direction. Let us say my receiver is here and they will be in the opposite direction. And continue further for another delay. After J, they come back to the same axis. They refocus here. Now plot the intensity for the CH2 carbon. Okay, intensity of the CH2 carbon as a function of tau delay. See, vector diagram you can understand in the same way. There is no difference at all. Only thing in this case is CH2 peak. In the CH2 case, central peak do not persist, and outer components start moving in the same direction. Again, resolve into two components and find out what happens as a function of tau. Everything will get the intensity plot like this. Now, when you plot the intensity as a function of TD, this follows like this again. It is not a cosine function. It is a function like this. Now, what is happening here? Exactly at TD is equal to 1 over J, 1 over 2J, it is 0. When TD is equal to 1 over J, this is positive maximum. What was the earlier case? You remember what happened to CH case? It was going like this and then it was becoming maximum, negative maximum. But here it is becoming positive maximum for CH2 carbons. You see the difference? When the CH carbon intensity was negative, at the same time, at the same point, CH2 carbon will have a positive intensity, negative, positive maximum. So CH2 carbon, you can monitor the change in intensity. It follows a cosine curve, but you see the cosine curve is not going like this. It is a positive. So it is following a different pattern. The maximum is now at 1 over J and minimum is at 1 over 2J. What happened to CH3 carbons? No difference at all, because CH3 carbons and CH carbon behave identical. Only thing is CH3 has 4 vectors because it is a quadret. 2 positive components and 2 negative components moving in the faster slow moving components. So two vectors will be there from the center to the right, 2 vectors from the to the left, that is 2 lines here, 2 lines here from the center. Again they follow the similar path like CH. You can trace it, both the components, how it is moving, you can trace it. It's behaving exactly like CH vector. So what happens is, if you trace it, it follows a path like this. So what did you observe? In the case of CH also, this was 0 at 1 over J and it was maximum of at 1 over 2J. Now same thing you are observing for CH3. So what did we observe, understand from this? What it means is, evolution, of course, is mathematically you can prove it. Evolution of CH follows a cosine path, CH2 follows this equation, CH3 follows this equation. But now when you put different values, pi is equal to, what is the value of this thing? For different values of pi and different values of tau, you can find out. When tau is equal to x 1 over 2J, what happens? When tau is equal to 1 over J happens, in this case of CH, when tau is equal to 1 over 2J, you put 1 over 2J here, this becomes 0. See, with 1 over 2J, tau is equal to 2J, J cancels out, pi by 2, cos pi by 2 is 0. You know that, that's why CH becomes 0. On the other hand, when tau is equal to 1 over J, this can cancel out, it is cos pi, so it's a negative maximum. So these are the equation which defines the intensity pattern. I did not go into the mathematics of it, it's a huge calculation. But remember, all the 3 equations, all the intensity as a function of tau for CH, CH2 and CH3 can be given like this. And as you plug in the values of tau, you know when it is maximum, when it is minimum. And varying the delay, what we understand in the spin sequence is, you can distinguish between 2 carbons, 2 types of carbons which are attached to odd number of protons and even number of protons. Same. The reason why it is, you understand what is going. Of course, J couplings are not same as I said. You have to assume nearly same or approximate value. Now, in this example, what did we understand? Take an example. I do that experiment, spin echo carbon 13. Now, if I keep on varying the tau delay as a function of J, what happens is CH and CH3 are negative and CH2 and quaternary are always positive for a particular value of J. You can find out what happens here at the 1 over J, this is the 0, 1 over 2J, this is negative. We will consider at 1 over J, what happens here? One of them is 0, we will not consider 0 component. We will consider only the signal which is positive or negative. Here, we consider exact at 1 over 2J, what happens? If you go to 1 over 2J, you see that CH and CH3s are negative. These are negative. CH2s and quaternaries are positive. What it means is the carbons which are attached to odd number of protons have one sign. Signal intensity is negative. Carbons which are attached to even number of protons or quaternary have one sign. They are positive. Of course, positive negative is my convention. I can interchange this. I can make this positive, this negative, doesn't matter. This how depends upon how I am doing the phase correction of the spectrum. So, but the difference what you should understand is CH and CH3 are opposite in the intensity compared to CH2 and quaternary. If these are positive, these are negative. So what it means is you are able to edit the carbon 13 spectrum using this pulse sequence, and you can say identify from your spectrum whether this carbon is CH2 or CH3 or CH. In a crowded spectrum, even after decoupling, there are, let's say, 30 carbons are there in the molecule, and you want to make the assignment. We don't want to take the coupled spectrum because it's complex. You do the decoupling, but then how do you assign? For assignment, we have to do some decoupling so that we know CH3, CH2, CH, doublet, quartet, triplet. But we don't want to do that. And this is the way, even after you can do the decoupling, you can understand and find out which carbon is which. But one difference, this is called attached proton test. This is called number of protons attached to carbon distinguishes the carbon, and this is called attached proton test. But there is one defect in this case. So it identifies this thing, but it does not distinguish CH and CH3. It distinguishes only odd number of protons attached to carbon and even number of protons attached to carbon, but does not distinguish whether it is CH and CH3 or quaternary as CH2. So that problem is always there. So that we have to overcome. Okay, this is a disadvantage. Now we'll go further, try to understand more about it, how we do and everything. We do what is called the polarization transfer techniques, where we can enhance the signal intensity. Here we were only looking at the identification of different carbons. Okay, you identify the carbon. You do this spectral editing. This is called spectral editing. Editing the spectrum to find out which carbon is which. But as I said, my problem of sensitivity is not solved. Still, carbon is less sensitive to detect compared to proton. So what do we have to do? We have to combine this editing technique along with polarization so that we can take the magnetization of abundant spin, give it to carbon, and also do the editing. We have a double advantage. We can distinguish carbons at the same time enhance the intensity. Can we not do that? It is possible to do that, and that's what we will try to do by using polarization transfer technique. So one of the ways of increasing sensitivity we know is to get more sample, do isotopic labeling, go to higher magnetic field, and record the spectrum at low temperature. All are practically possible or not possible. Sometimes depends upon your ability, what you can do, whether you have more sample or whether you have facility to do isotopic labeling by some chemical way. Sometimes it's very expensive. For going to very higher magnetic field, if you want to get 800 megahertz or 1000 megahertz spectrometer, it may not be possible, there may be not be available. So all those limitations are there. So let us understand, in addition to this thing, how can we play with spin dynamics and design new NMR experiments. Okay. What we do is, when you ask the question, how do you do the polarization transfer, take the population difference from a sensitive nucleolite, more sensitive nucleolite proton, and give it to carbon and nitrogen. There are two ways of doing this. Okay, remember, One is selective population transfer, other is selective population inversion. How these two techniques will enhance the signal intensity, let us understand today. Okay, this is called polarization transfer technique. Please remember, there are two polarization transfer techniques. One is selective population transfer called SPT. Other is selective population inversion called SPI. These techniques, if you understand, we can couple with the editing technique later. Now let us go to population inversion scheme. What is a population inversion? How does it enhance the signal intensity? Now let us consider homonuclear spins, two weakly coupled protons. We'll come to carbon 13 later, because finally our idea is to enhance carbon 13 signal intensity, not protons. Anyway, protons are both abundant. Okay, if I take homonuclear coupled, but just to give you the feel, how much is the gain in the signal to noise ratio when you take carbon and proton instead of when you're in relative to proton and proton, we'll see. Now I consider an example of two weakly coupled spin systems. I have already discussed with you weak and strongly coupled. What are the weakly coupled spin systems and what are the strongly coupled spin systems? And two weakly coupled spin systems are there. When there are two protons are weakly coupled, you have only 4 energy levels. That's what I said, 4 transitions, 4 energy levels and 4 transitions. No doubt about it. We have discussed this a lot, and all of them are equal intensity. We know that, and we know the center of this gives a chemical shift. This gives chemical shift. This separation gives you J coupling. I don't have to repeat again and again. I hope you are all with me. This is called AX spin system. AX spin system gives 2 lines for each spin of equal intensity. Now we will understand based on the population in thermal equilibrium. Let us have 4 energy levels. You all know it's alpha alpha, alpha beta beta, alpha beta beta, 4 energy states. I'll now put spins in each energy state to ensure that population ratio is such that the intensity is always equal, because that is what the weakly coupled spin system is all about. Okay, all we should get equal intensity. For that, what I'll do is I'll take 4 spins here, just for the sake of understanding. 2 here and 2 here. Now what is going to happen? Look at the population differences to get the intensity of the signal. What are the allowed transitions? We have already worked out for AX spin system. Beta beta to alpha beta, change in the magnetic quantum number is +1 or -1 allowed, and this is allowed, this is allowed, this is allowed. There are 4 transitions allowed, and this correspond to I peak, I intensity, I peak. This correspond to peak of I spin, because I and S if I take here, I is getting changing from alpha to beta. Similarly here, I is changing from alpha to beta, and if I take S here, S is changing from alpha to beta, and here S is changing from alpha to beta. So I have labeled the spins based on their spin states alpha beta like this. Now to calculate the intensity, I take the population difference. That's what I said. Detection of the NMR signal is nothing but the difference in spin populations. Now for S transition, this is allowed. What is the difference between 4 minus 2? 2. Okay, intensity is 2 for S. Another S transition, 2 minus 0, it is 2. For I have put 2 and 0. This is allowed transition for I. 2 minus 0, 2. Another I, 4 minus 2, 2. So I have distributed the spin population so that I must get the spectrum with equal intensity. But it is only for rough estimate, only for understanding purpose. Don't think there is no signal, no spin at all in the state. There are spins, large number of spins distributed among all the spin states. Finally, it so happens when you get the transition, there are equal intensity. Only for understanding and calculation purpose, to make my calculation simple, I have taken this. Never be under the impression there are no spins in the beta beta state. That's wrong. Okay, that is not the case. There is spin present in the beta beta states also. Now what I am going to do is I'll do a trick. I am going to irradiate and saturate only one of the lines. You know what is irradiation? That's what I said, decoupling. decoupling we use sometimes called irradiation. I do the irradiation. When I irradiate, I can saturate the spins. What I mean by saturation? I make the spin states, population between two spin states equal. Now, I am doing this saturation I spins level 1 and 3. What is the I spin here? Here. Level 1 and 3. Okay. Look at this. Level 1 and 3 I equal. When I equal it by saturate, what will happen? This was 4, this was 2 spin. They become equal. Then there are 3 spins here and 3 spins here. They will distribute equally between these two so that there is no population difference. That is called saturation. Now when I do saturation, look at it, they are equal. That's all I did, nothing else. Only one of the transitions I am saturating. Okay, now let us see what is the intensity. You calculate. This is 0. Now if I transition, because I am saturating, it should happen. The saturated peak always do not come. It gives 0 intensity because there is no population difference. What about other I spin? This one. Okay, take the difference, it is 2. That has not changed. I agree. What about S spin? S transition is here 3 to 2, difference 1. And this one, S transition 3 to 4 is 3. Fantastic, is it not? What did we do? You saturated only one of the transitions and see the effect is there on other transitions. This transition did not get affected. I did disturb I spin energy state, I spin population, but S spin is also getting affected. See, this intensity came down by half. It was 2, 2, 2, 2 all along, in the previous case. All were equal intensity. Now this became 1 and this became 3. This one. Fantastic. When I recalculate the intensities, I find now the population distribution is such that the intensity when I saturate I spin is affecting S spin also. Now there is 0, 2, 1 and 3. So fantastic. Now this what happens. Let us wait for some time. I did this type of disturbance, saturation, I do for a short time by applying a weak RF. I cannot apply a strong RF because every spin system, all energy states can be disturbed. I don't want to do that. I apply selectively only for this transition. By a weak RF, mild RF I apply and disturb only this for saturation and keep quiet. That's what I did. And after some time, I remove the RF pulse. What will happen? When I remove the radiation, this was a disturbed state. What should happen? The spin has to go back to thermal equilibrium. Exactly. Go back to previous case. Population 4220. It has to achieve that. So that it comes to thermal equilibrium with intensity 2222. This happens after some time. How much time it takes? We all know what is going to happen for time for relaxation, everything. This is a different type of relaxation after applying. So we will now come to the relaxation later. But remember, I saturated and removed the RF pulse after some time. The spin system go back to thermal equilibrium. What did you achieve now? Changing the population of the one spin of the spin system by doing selective population. This is saturated selective population transition saturation. You achieved change in the intensity of the coupled spin. Of course, they must be coupled spins. So what did I do? I saturated one of the coupled transitions. I observed the change in the intensity of the other spins. This is a fantastic thing. So this what is the thing we achieved. This is called selective polarization transfer. Why did I do that? Why we call it? Selectively I saturated only one of the transition. I did not saturate uniformly like in heteronuclear decoupling. All protons are saturated so that you don't see coupling with carbon. That is a uniform broadband decoupling. But here only selective saturation. See the beauty of NMR. You can play with even a one single peak, single transition can be saturated. So this is causing change in the intensity of coupled spin. This is called selective polarization transfer. On the other hand, we can also do the selective population inversion. What is population inversion? In the case of saturation, we are equating the populations. Okay. In the case of selective population transfer. Now let us do in a different thing. I apply a pi pulse on a particular transition. What does pi pulse do? It will invert the populations. Like magnetization which was here was brought here. This is 180 pulse, right? So 180 pulse inverts the spin populations. So what it does is an inversion pulse. The populations, instead of saturating, I'm inverting in between these two. Same transition I took. When I saturated, it was 3-3. Before saturation, it was 4-2. After saturation, it became 3-3. Now in the inversion, the 4 which was here went here, the 2 which was here came back. Just population between these two states got interchanged. That's all I did. This is called selective population inversion. Now let us see the intensities. Recalculate the intensity. What is intensity of I spin? I spin from here to here. This is 2, this is 4, it became -2. Earlier it was 2, 1:1:1, 2:2 was there. Now you see, if I take the population difference between 1 and 3, it is -2. Go to 2:4, it is same 2, it is not changing. What about 1:2? 1:2 population is 0. This is 2, this is difference is 0. So 1:2, I am not disturbing this spin, remind you. I am not disturbing things, I am only disturbing this transition. I am not doing anything for this S transition, but I made this signal 0 by doing selective population inversion. You understand what is happening? Now consider transition 3-4. So this is 4, this is 0. What is the population ratio difference? 4. So what is the intensity ratio now? -2, 2, 0, 4. Fantastic. I inverted one of the transitions I spin and enhanced the signal intensity of the other one, coupled spin, by 4, factor 4. Of course, this has come down. We will worry about it later. But what it means is this experiment also changes the intensity. There are two ways of enhancing the intensity of the coupled spin. One is selective population transfer. Other is selective population inversion. In the selective population transfer, you equated the spin population, that's called saturation. In the selective population inversion, particular transition populations are inverted in between the energy states. That's all we have to do. Okay. Now, that was for homonuclear. I wanted to see the difference for you. Now let us see what happens if you apply in a heteronuclear case. This is what our interest is. Finally, we want to see the enhancement of the carbon signal, not proton, right? The intensity of the carbon signal is 4 times less than that of protons. Remember, I gave you the energy level diagram of homonuclear spin coupled spin system. Two coupled, in one of the classes where homonuclear energy levels are equal, heteronuclear are very well separated. Two small energy states for hetero and large energy separation for homonuclear spin. I wrote it very clearly. That is coming handy now. Please understand, that becomes very useful now. Now the same way we write the energy level diagram. Now instead of I and S, I am writing I as proton, S as carbon 13. Both are homonuclear there. I wrote I and S. Now it is heteronuclear. Instead of writing I and S, I am writing this as proton and this as carbon. So again, heteronuclear two spins coupled invariably has to be weakly coupled. There is no doubt about it, right? We have been discussing this quite often. So now let us arrive at the population distribution. As I said, carbon 13 is less sensitive, 4 times less intensity compared to proton. So I have put the populations in a different manner here. In the case of proton, it was 4-2-2-0, so that everything become 2-2. All 4 transitions of equal intensity. But now I have deliberately made this such that carbon intensity should be 4 times larger. I'm sorry, 4 times smaller. That is because carbon gamma is 4 times smaller. Okay. Now let us see what is intensity. I put 10 spins here, 8 here, 2 and 0. Okay. What is the advantage of that? See the difference now. What is This one, proton transition, one difference between 1 and 2 is intensity 8. What is proton transition? 3 and 4. 8 minus 0. Intensity is 8. What is carbon transition? 2 minus 0. 2. Here, carbon transition, 10 minus 8. 2. Now you understood why did I choose different spins here? 10, 8, 2 and 0. Because now compare the intensity ratio. 2 to 8, 8. Proton intensity is 4 times larger than carbon intensity, which are 4 because of lower gamma. Deliberately I wanted to choose this. Now see how much was the gain in the signal intensity for selective population transfer and selective population inversion for understand now. Okay. Now we will see only saturation transfer. What happens? I am going to saturate one of the transitions, that is 1 and 2. Proton transition I am saturating. What was the population difference? 10 and 2. Now 10 and 2 is totally 12. I made it 6, 6 because I am saturating. I am equality. So it was 10, it was 2. I equated it 6, 6. That's all I did. Now calculate the intensity. Proton is, this is saturated signal will not give signal 0. And this signal 8 minus 0, it is 8. That is not changed. Look at the carbon now. This is 1, this is 6 and 8, this is minus 2. What about other one? 6 and 0. 6 minus 0, it is 6. What a marvelous change in the intensity. I saturated one of the proton signal and the carbon signal, there is a one of the peak has enormous rise in the intensity. Instead of 2 to 8, 8, it becomes 6, 3 times enhancement. Okay. That's what, there is a threefold enhancement of the signal of one of the carbons. Okay, let us see population inversion also what happens. First remember, we'll come to the population inversion now. You understood the selective population transfer in the heteronuclear case, similar to homonuclear case, there is a rise in intensity, but there is a more rise in intensity here because we are considering heteronuclear and you see one of the peak goes by threefold in intensity. What I will do is, I will stop now, come back and continue the heteronuclear selective population inversion, then go to inept sequence and then depth, so that all these editing techniques will be understood. Because inept and everything is very useful in all the 2D experiments like HSQC and others. Whenever you want to do polarization transfer, these modules are used. So we'll come back, understand this thing and continue further tomorrow.